In this lesson, we're looking at double angle formulas. In order to develop the double angle formulas, we're going to be using the compound angle formulas. What I'd like you to do is take these compound angle formulas, substitute theta in for A and B, and see if you can simplify them. Then come back and see how you did. The sine of theta plus theta is equal to sine theta cos theta plus cos theta sine theta. Simplifying on the left side, that would be sine 2 theta, which is our double angle. And on this side, we have 2 sine cos thetas. So we can simplify this by putting a 2 in front and sine theta cos theta. So this is one of our new double angle formulas. Looking at the cos compound angle formula, cos theta plus theta equals cos theta minus sine theta sine theta. Similarly, we can look at this and write cos 2 theta equals, and what we have is a cos theta squared. Now I'm going to introduce a math convention where we don't put brackets when we square trig ratios. Instead, we put a 2 right here. So we have cos theta squared minus sine theta squared. And that's our next double angle identity. And finally, looking at tan theta plus theta is equal to tan theta plus tan theta all over 1 minus tan theta times tan theta. Simplifying, we have tan 2 theta equals a tan theta plus a tan theta is 2 tan theta all over 1 minus tan theta times tan theta is tan theta squared. And there's our third double angle formula. At this point in time, we're also going to look at another relationship, which isn't actually a double angle relationship, but it's an important one, and so it's going to be included in this lesson. When we look at sine theta and cos theta, we can look at them in terms of Pythagorean's theorem. If you look at this diagram that's here, you will see that we could write sine theta and cos theta in terms of x, y, and 1. So in the first case, sine theta is equal to the opposite over the hypotenuse, which is y over 1, which simply equals y. In the second case, we have cos theta, which is the adjacent over the hypotenuse. That gives us x over 1, which equals x. Summarizing, we have y equals sine theta and x equals cos theta. Thinking of Pythagorean's theorem, we could look at this triangle and write x squared plus y squared equals 1 squared, which is 1. Now what we'll do is replace the x and the y with the trig ratios. Cos of theta squared plus sine of theta squared equals 1. So that's another useful identity for us that allows us to simplify a number of expressions where we can get them to equal simply 1. We can also rearrange these. Sine squared theta would be equal to 1 minus cos squared theta. Cos squared theta would be equal to 1 minus sine squared theta. We get that from taking this expression here and, in one case, subtracting cos squared theta from both sides to end up with this, and in the second case, subtracting sine squared theta from both sides to get this second expression. To summarize these identities, we have sine theta equals 2 sine theta cos theta. Tan 2 theta equals 2 tan theta all over 1 minus tan theta squared. And cos 2 theta equals cos theta squared minus sine theta squared. Now, in this case, it's not uncommon for us also to write the cos 2 theta formula in two other ways using the relationships that we just found with Pythagorean's theorem. First of all, we can take cos 2 theta and make it equal to 1 minus sine squared theta. Here we're replacing cos squared theta. And then we have minus sine squared theta. That equals 1 minus 2 sine theta squared. The other way that we can rewrite this double angle formula is to replace the sine squared theta. We will have cos squared theta minus bracket 1 minus cos theta squared equals cos theta squared minus 1 plus cos theta squared equals 2 cos theta squared minus 1. So these are the other two representations of this particular formula. Now we can take these double angle formulas and we can apply them as we've done before in terms of simplifying. Two sine 3x cos 3x. In this case, if we think of 2 sine theta cos theta, that comes from sine 2 theta. Theta, in this case, are the three x's here. So what we're saying is that theta is equal to 3x. This then can be written as sine 2 of 3x, and that equals the sine of 6x. We can do something similar with this identity over here. Looking at this expression, we know that tan 2 theta equals 2 tan theta all over 1 minus tan squared theta. So what we're saying here is that theta is pi over 2. This expression can be boiled down to the tan of 2 times theta, which in this case is pi over 2. This equals tan of pi. Applying these relationships in the other direction, sine 6 theta, if I want to represent it as a double angle formula, would be sine of 2 times 3 theta. Those two expressions are equivalent. But we know with the relationship that we have for sine 2 theta that this would be equal to 2 sine of the angle that's being doubled, so in this case 3 theta, cos 3 theta. And that's the other way of representing this. Similarly here, this can be written as the cos of 2 times 4 theta, which would make this equivalent to the cos of 4 theta squared minus the sine of 4 theta squared. And as we saw earlier, there are two other ways that I could represent this as well, but this is sufficient for us to show how we can use this double angle formula in this case. In this final example, we're going to show how we can take an exact value that we already have been given and use that to take a double angle expression and find the exact value solution for it. To do this, we're going to need a diagram to represent this relationship here with sine theta equals 5 over 6. Using our cast rule, sine theta in this case is positive. We've also been given a range of pi over 2 to pi, which agrees with the cast rule where sine is positive in this quadrant. So we'll draw a triangle in that quadrant. The opposite would be 5, and the hypotenuse would be 6. Sine theta is opposite over hypotenuse. In order to be able to write the other trig ratios, we may need this third side, so we'll use Pythagorean's theorem to get that side. Using the xy coordinates, this side would be the x. X squared plus 5 squared is equal to 6 squared. X squared plus 25 is equal to 36. Subtracting 25 from both sides, or bringing the 25 to the other side and changing its sign, we end up with x squared equals 36 minus 25. X squared equals 11. So x is equal to the square root of 11. And there are no perfect squares that go into 11, so I can't simplify that any further. That makes this side minus, due to its position, the square root of 11. Starting with sine 2 theta, once again, sine 2 theta is equal to 2 sine theta cos theta. We already know the value of sine theta, but we don't know the value of cos theta yet. If we look over at this diagram, cos theta is negative the root of 11, the adjacent, over the hypotenuse, which is 6. Substituting into the formula, 2 sine theta is equal to 5 over 6. Cos theta is equal to minus the root of 11 all over 6. Simplifying, we can cancel or reduce this fraction. 2 goes into 2 once, and 2 goes into 6 3 times. That leaves us with negative 5 root 11 all over 18. Coming over to tan 2 theta, we can do something similar. Tan 2 theta, recall, is equal to 2 tan theta all over 1 minus tan theta squared. Looking at our diagram, tan theta is equal to the opposite over the adjacent, which is 5 over negative root 11, or negative 5 over root 11. I won't rationalize this yet. I'll do that at the end of my question. This leaves us with 2 times minus 5 over the root of 11 all over 1 minus 5 over the root 11, and that's a negative, squared. Simplifying, I now have minus 10 over root 11 in the numerator. And in the denominator, I have 1 minus 5 squared is 25, and root 11 squared is 11. Now I need to continue simplifying this. I'm going to carry on at the top here. Minus 10 over the root of 11 is equal to 1 is the same as 11 over 11. So 11 minus 25 is minus 14, all over 11. At this point, I need to invert and multiply. Minus 10 over the root of 11 times minus 11 over 14. I'm dividing by a fraction, so I'm multiplying by its reciprocal. And because the whole fraction is minus, I was able to simply put the minus out in front and reverse the numbers. Multiplying the numerators, and keeping in mind that a minus times a minus is going to be positive for this fraction, I have 10 times 11, which is 110, and 14 root 11. The final step is to rationalize. I need to multiply the denominator by root 11 and do the same to the numerator. That leaves me with 110 root 11 all over 14 times 11 equals 154. Now you can go ahead and try the practice.